Hello and welcome to a new lecture on artificial intelligence. In today's lecture, we are going to study fuzzy logic. Fuzzy logic is under the category of knowledge, reasoning, and planning. Under category of knowledge, reasoning, and planning, we have logical agents which are first order logic, planning and acting, knowledge, representation, inference, ontology, probabilistic reasoning, and decision making. The word fuzzy means ambiguous, ambiguity or vagueness, not clear, not exact, not precise. Fuzziness occurs when the boundary of a piece of information is not clear. So in this lecture, we will study fuzzy sets, history, uncertainty, fuzzy logic, application, membership function, fuzzy operation, and fuzzy type 2. In the course of discrete mathematics, we study a concept of set theory. In set theory, we deal with different types of sets. What are sets? Sets are considered as the building blocks for the type of objects considered in discrete mathematics. So we can simply say set is an unordered collection of things or objects or people or whatever you can think about. For example, the set of students in class, one set. Set of natural numbers, integers, real numbers, complex numbers, rational numbers. These are sets. In a broader category, we can classify sets in crisp sets and fuzzy sets. In crisp set, an element is either a member of a set or not. For example, if this is set A, and here this is A, and this is B, A is in A, but B is not in A. This is called as crisp sets. There are several operations that we can apply on sets, right? Complement. If this is our universal set, then U minus A is called as A complement or A naught. B belongs to A naught. Or we have containment. This A is a subset of B because all the elements of A belongs to B as well. Or we can think about intersection. Or you can say common places. This part is common between A set and B set. Or you can think of union. So we can say A intersection B, right? Or here, union, we can say A plus B. Whatever is in A and B. In here, we say X in such cases that X belongs to A and X belongs to B, right? This is AND. It means one element which belongs to both of them. In here, we say X's in such a way that X is in A or X is in B. This is OR function. It means if it belongs to A, is okay. If it belongs to B, is okay. If it belongs to both of them in this part, also okay. This is called as union. The classical set or crisp set developed by this gentleman, George Cantor, in 19th century, and there are many operations for these cases. If we consider X as the universal of disclosure, or you can say universal set, then we say X in X. Then in classical set theory, crisp set of A, for example, is defined as FA and X 0 or 1. It means one element belong or does not belong. This function maps universe X to set of two elements. If we say 1, if X belongs to A, or 0 where X does not belong to A. For any element X of universe X, which we say F, A, X, if belongs, we show by 1. If does not belong, we show by 0. However, in order to solve some specific problems, crisp sets are not helpful for us. Experts rely on common sense when they solve problems, human common sense. How we can represent expert knowledge that uses vague or ambiguous terms for computer systems using crisp sets. Fuzzy logic is a solution. Fuzzy logic is based on the idea that all things admit some degree. For example, temperature, height, speed, distance, beauty. When we say someone is beautiful, how you can say he is beautiful? In terms of precise, we should introduce computer then what is the meaning of beauty. When we say something is hot, or someone tall. For example, one guy, his height is 100 centimeter. We say he's tall. Another guy is 180 centimeter. Again, we say he's tall. Another guy is 190, 200, 210, 20, something. We call them all tall. But how we can tell computer what is the meaning of tall here? These are not equal. 170 is not equal to 180, 190, 200, 220. These are not equal. Or, for example, this color is white. This color is white. This color is white. This color is white. This color is white, this color is white, this color is white. We human beings, we call them as white, but they are not equal. So the problem is here how we can teach computers to distinguish these linguistic words. Or, for for example, in this figure, and there is a problem, the common sense, just we say, look out. Look out means 1,500 kilograms of mass is approaching your head. We don't say this thing to just one word he can understand. But how about computers? Computers do not understand like human being. We need to think about fuzzy logic. What is fuzzy logic? Fuzzy logic has been introduced by this gentleman, Lutfi. And the most interesting thing to know about the founder of fuzzy is when people ask him, where are you from? He said, I'm fuzzy. I can't say exactly where I am from because my nationality is fuzzy. How? Because he was born in Baku, Azerbaijan, Soviet Socialist Republic. His father was from Iran. His mother was Russian, but originally Iranian. Up to the 5th degree, he was in Azerbaijan. Then he moved to Iran and he studied at the University of Tehran. Then he moved to US, MIT. Then he went to Columbia. Then he went to Berkeley and finally in California. So when people ask him, where are you from? He said, I don't have an exact answer to you that where I'm from. 10% from Azerbaijan, 10% from Russia, maybe some percentage from Iran, he was also in Germany, some percentage from US. Fuzzy logic is a set of mathematical presentation to knowledge representation. As I told you already, we are going to talk about knowledge presentation and how we use the concept of degree of membership. Unlike two-valued Boolean logic, fuzzy sets are multi-valued, and fuzzy set deals with the degree of membership function and degree of truth. In here, we use the continuum of logic values between 0, which is completely false, and 1, which is completely true. But between 0 and 1, we have many, infinity. In there, increase, we said A belongs to A, 0 or 1. 0 means not, 1 means yes, okay. But in here, we say A belongs to A with some degree of membership, 5%, 10%. We say this color is 100% white. This one is 90% white. This color is 30% white. This color is 80%. This color is 30% white. We don't call them fully white. What percentage? This one is 100% white. We consider some intensity between 0 and 255. When it is 0, we say it's black. When it is 255, we say totally white. So this is 0%, this is 100%. And between, from 0 to 255, we have infinity degree of membership. Instead of just black and white, fuzzy employs the spectrum of colors. They accept the things that can be partly true and partly false at the same time. Let's look at the history of fuzzy logic. In 1965, a seminal paper. Seminal means very famous paper, very well accepted paper by experts. And it has been published by Zadeh in 1965. He was at that time faculty of electrical engineer at the University of Columbia, Berkeley. And he talked about, set the foundation of the fuzzy system theory. Then in 1970, the first application of fuzzy system was in control engineering in Europe. In 1975, in Japan, they used for Sunday train. Then in 1980, we had seen empirical verification of fuzzy logic in Europe. Then later in different countries, they talk about it. In 2000, we had seen that fuzzy logic becomes a standard technology and also applied in data sensor signal analysis and many other applications. Most words and evaluation we use in our daily reasoning are not clearly defined in mathematics manner. Such kind of ambiguity allows humans to reason on some abstract level. To represent uncertainty to computers, we can think of two uncertainty, stochastic uncertainty and lexical uncertainty. Both are uncertainty, but stochastic or random, by some chance, and this is normally by word. Lexical rises from either an ambiguous definition or incorrect use of a word or words in context experienced by language users. The stochastic and fuzzy logic complement each other. For example, when we say the probability of hitting target is 80%, you want to shoot and you say that it will touch it by 80%. I can't say absolutely yes or absolutely not. But in lexical uncertainty, when we say a man is tall or today is warm or hot and stable condition, or we will probably have a successful business here. Fuzzy logic is not so popular today compared to deep learning and machine learning, but still we can think of many advantages. Using fuzzy, we can mimic human control logic. We can talk with computer using imprecise language. We can think about having robust techniques. We can, think about the, when there are some problems, how safe it can be, and also simply we can modify the models. One of the great applications of fuzzy logic was Sendai Subway. The Sendai Subway is a rapid transport system in Sendai, Japan, and it is for multi-unit trip type operated on Sendai Subway in Japan. This is somehow the world's first system that they use fuzzy logic to control the speed. This system was somehow developed by a company Hitachi, and it was for the relative smoothness of the start and stop of the trains. There are many other applications for fuzzy logic, like anti-sway crane controller. Anti-sway means how to take care of balance. And for flexible robots, also need the fuzzy system to manage their balance. Another application is fuzzy washing machine. Using fuzzy systems, these machines can optimize their performance and hence decreasing time and electricity usage. For example, if you have 2 kg, they need, for example, 30 minutes to wash. But if you have 9 kg, then they will have 90 minutes to wash. So how to optimize? And others like robot skating, aerospace, autonomous cars, and many other things. This graph shows the scope of current fuzzy society. In the application level, we may think of clustering, statistic, pattern recognition, and data processing. And for that one, you can think of fuzzy relation, fuzzy number, extension principle, and fuzzy optimization. In the case of measurement, fuzzy integrals and fuzzy measurement can help us for decision-making, evaluation, estimation, and expert system. And also fuzzy logic using linguistic variable, fuzzy algorithm, and approximate reasoning, they can help fuzzy controls. Normally, elements of fuzzy sets are mapped to a universe of membership values. And for that, we use a function theory 4. So we denote fuzzy sets like A tilde, this one. And we say that this A tilde is a fuzzy set of A using this operator. Some people also, they use A hat, that's correct. This function maps elements of a fuzzy set, this one, to a real number which is between 0 and 1. 0 and 1. And there are infinity possibilities. If an element in the universe, for example X, is a member of our fuzzy set A tilde, then this is mapping by this function. And this one we call as membership function. As you can see later, I will talk more about this. Let's see one example to better understand the fuzzy sets. If we consider a fuzzy set of real numbers close to 10, right? It's a fuzzy set close to something. And what is the meaning of close? This close is fuzzy. Because in here, 9 is close, 9.1 is close, 9.7 is close, 9.9 is close, but different close. All are close, very close, almost close, exactly close, far close, less close. This is called as fuzzy. So this is our universal set, the set of real numbers, and then we can define our membership function for this one, A tilde R, and we define in this form. And as you can see the graph here, 10, the membership function is 1, the core. Then here, 0 and 20 are not close to 10. This part, for example, this part and this part, these are very close. This part is, you can say this part is close. This part a little close, right? And also the same here. And also, we want to see how we use notation of fuzzy sets if two possibilities are there, discrete and finite, continuous and infinite. When the universe of this clause is discrete and finite, then our fuzzy set will be something like this. Mu A x1 divided by x1 plus mu A x2 divided by x2, up to when we can use this summation, mu A xi divided by xi. And in the case that x is continuous and infinite, then our fuzzy set will be integral. So here we use summation because it is discrete. But here we use integral. So in this figure, we can see the membership function. The maximum value is 1, the minimum value is 0. Now, let's see the difference between crisp set and fuzzy set in mathematical representation. In crisp sets, we deal with characteristics function, as you can see here. But in fuzzy set, we are working with membership function. In here, it says to us that a member belongs to a set or not. As I told you already, this one is not, and this one is in. But in here, the degree, based on the equation that we already had for our close to 10, 1 plus x minus 10 to the power of 2, then we can go for this one. So this blue color, we already saw it, right? This blue color, number close to 10. The green color is roughly close to 10. So in order to do that, we need to specify 3 points. This is A, this is C, and 10 is our B. Then how we plot it? If, for example, A is equal to 5, B is equal to 10, and C is equal to 15. If it is less than or equals to 5 and greater than 50, it is 0, as you can see here. If it is between 5 and 10 for this part, we use this equation, x minus A divided by B minus A. And for this part, we use this equation, C minus X divided by C minus B. And for this one, which is very close, then we can go for square of mu A. In conventional or Boolean set, we clearly and explicitly talk about elements. For example, if we talk about fever of someone, fever, right? So we can say someone has a fever, up to some degree, fever, right? Well, how you can say strong fever? 37.2 is okay, 38 is also okay. But when it comes to this area, it is strong fever. But in fuzzy, we define with membership function. We say that if someone has 42, he is absolute fever, right? Very strong. In this part, strong. This part, less strong. This part, nothing. So in fuzzy set, we deal with more or less rather than either or. In fuzzy set, we deal with degree of membership. And after that, an element, we can say it belongs to a set using a certain degree. For example, if we define this set as strong fever, then we say 35 belongs to this with the degree of 0. 36 belongs to a strong fever, it means it doesn't belong. It's not in, right? Not in, right? Not in. Then we say 38 with a 10%. This one equal to 10%. So 38 fever, centigrade fever is 10% strong fever. 40, 65%. 41, 90%. 42, 43 is absolute strong fever and the guy may die, right? So in this way, we show, and here is the graph. Up to 37.7, the degree is 0. From 41 up more is absolute, and in this between there is some degree, as you can see here. Here are some other example. For example, this one is like ceiling function, you know, ceiling function. So if it is less than t or equal, right, then it is 1. Otherwise, it is 0, like ceiling function. So up to here, it's 1, then it is like 0. And this is another one, CA 1 by 2 1 plus cosine A pi. As you can see, this is also can be a membership function. Later, you will see that this is called as Gaussian. Now, we need to learn some characteristics of fuzzy sets. A fuzzy set is called as supremum, you can say SUP, if it is equal to 1, the max one, right? The maximum. For 10, it is 1 here, right? It's maximum. It is potential maximum, like a global maximum. May it is there or may not there. But we have maximum. The maximum is something that already got. Supremum means potential, or you can say global. But maximum is what we achieved. You can say local. And if you want to normalize, simply we do it by dividing the membership function by the supremum of the set, which you can see here. This like this, we can normalize a set. Here are some other properties of fuzzy sets. The first one is the support of fuzzy set. The support of fuzzy set will denote by CUP, right? Then it's a crisp set of all x for which membership is more than 0. This supremum is different. Supremum is, support is shown by SUPP, like this. And it is where the membership is more than 0. So if this is our membership function, this point is support, supremum, but this part is support. Whole part is support. Then this part, this value where we have supremum, this value of under x is called as core, where the membership is 1. Then we have boundary. Boundary of fuzzy set is a crisp set for which mu x is between 0 and 1. 1 is not included, 0 is not included. Then we have alpha level set. For alpha level set of, for example, this 8 we have shown where it is less than some specific value. For example, cut 2.2, cut 0.4, something like that, right? We say alpha. And also, strong alpha cut is a crisp set when it is greater than alpha. So this is greater or equal, this is absolute grade. Using one example, we can better understand the topic. We want to see how many rooms are needed for a 4-person in a house. If we have 4 people, the best case is to have 4 rooms. The best case is to have 4 rooms. If it is 1, it is 10% good. If it is 2, it is 50% good. If it is 3 rooms for 4 people, it is 80% good. But 4 rooms for 4 people in one house is 100% good. And again, 5, 70%, 6, 20%, 10, 0. Then if you want to talk about A cuts for this set, we say 0.1. So 0.1 from here upward, 1, 2, 3, 4, 5, 6. Then 0.2, 1 is not included because we start from here, alpha cut. Then for 0.5, we again start. So you can see 0.5 and 0.2, but this one is not included, right? For 0.7, we will consider these 3, 4, and 5. For 0.8, we will consider these 2. And for 1, we consider only 1. So here, there is alpha level sets. It's a kind of theorem. It can be proved that for a fuzzy set of A, then the union of alpha is alpha multiply A alpha, which means that any fuzzy set can be written as the union of all values of a alpha of the product between alpha and alpha cuts of the fuzzy set. This property is important and it connects the fuzzy set and crisp sets. And also, it is very useful for proving different properties of fuzzy sets. A fuzzy set have some operation like what we have in crisp sets. If we have U, this is our universe of discourse, and F and G are fuzzy sets on U, then F is equal to G, we call it as identity if their membership functions are correspondingly equal. And also we call F subset of G if the membership function of F is less than the membership function of G. This mu F we simply call that affiliation, for example. Or you can say membership function. Mu of FUG is the maximum of one of them. Which one is more? So here 2 examples we have, and this is the degree of G. Then in order to come up with the union, we will consider which one is more. So 1 and 1, 1 and 1, same. 1 will come here. 75 for 1.5 and 6. So this will be selected. 0.3, 0.2, 0.3 will be selected. 0.15, 0.1, 0.15 will be selected here. And 0, 0, same, 1 will select. So the maximum will come. For union, we will call the maximum. On the other side, for intersection, we will consider the minimum. 1 and 1, 1 will come. 75, 6 will come. 0.3, 0.2 will come. 15, 1 will come. And 0, 0 will come. Then we have a fuzzy complement. We show by FC or tilde F or F naught, something like this. All elements in the universe that do not belong to F, right? And how we show 1 by membership value of F. So how we do it here, if this is our F, then F complement or FC, you can say FC or tilde F, then 1, 1, it means 1 minus 1 is 0. 1 minus 0.75 is 0.25. 1 minus 0.3 is 0.7. 1 minus 0.15 is 0.85. And 1 minus 0 is 1. So this is a complement. For the G, also we do the same. 1 minus 1, 0. 1 minus 0.6, 0.4. 1 minus 0.2, 0.8. 1 minus 0.1, 0.9. In this case, we can find a complement. So here are some axioms for fuzzy complement. C of 0 is 1, C of 1 is 1. And the second one is motonicity. For all A and B belongs to 0 and 1, if A is less than B, then C of A is greater than C of B. And for continuity, we say C is continuous function and C of CA is simply A. It means what? As you know, complement of complement is A. Difference is the minimum of degree of the first function and complement of the second function. You can see here. If we want to find the difference between F and G, first we need to find the complement of G. So this one and this one means here 75 and 4 will be 0.4 will be selected, 0.3 and 0.8, 0.3 will be selected, 0.15, 0.9, 0.15 will be selected, 0 and 1, 0 will be selected. Here are some properties of standard fuzzy operators. Complement of complement is F. F union G, no difference between G union F, doesn't matter. We call it as commutative. F intersection G and G intersection F, the same, doesn't matter. Then we have associativity. F union G union H is the same. It means it doesn't matter when we move the parentheses. So in discrete mathematics, you already learned these things. Distributivity, so in here you can see that the operator is the same, but in here different. So if you want to distribute F union G intersection H, then it will be F union G intersection of F and H, the same way we do it here. And the last one, F union F is F, F intersection F is F. Here are some other properties. F union F intersection G is F. The same thing this side. F and phi is empty. F intersection phi. F union U is the universal, is U. F union phi is F, F intersection U is F. The Morgan law, we want to find the complement of 2. This changes. So F intersection G complement is F complement union G complement. And here in equivalences, F complement union G intersection with F union G complement is F complement intersection G union with F G. And here is symmetrical difference. F complement G intersection and F intersection G complement is intersection of F complement union G complement and FU. Almost the same as Chris said. The intersection of F and its complement is phi. The union of F and its complement is a U universal. And disjunctive sum. So we say that this F sum circled, you can call this one sum circled, is F intersection G complement union F complement intersection G. And here are the some others. So all are like the Chris said we studied in discrete mathematics. Here are bounded sum F theta G. F theta G tell us the minimum of 1 and membership function of U F plus mu G. It means it should not be more than 1. This is somehow boundary. It does not let it go more than 1 because the maximum should be 1. And here F dot circled is maximum of 0 and the sum of them minus 1. Then here we have product of fuzzy set for H, F square membership function of this one, which is square of that one. So Cartesian, like the same that we have, we find out the minimum degree function of all of them. So far in this lecture we learned about fuzzy sets. Now we want to learn the main components of fuzzy logic, and one of them is membership function. So membership function is the values that we assign to the elements of the universal set, which is something between 0 and 1. So these are specified range, and this indicates the membership grade of these elements in our set. When we have larger values, it means the degree of our set is more. So a set defined by membership function is called as fuzzy set. The most commonly used range of membership function is 0 and 1. The universal set X is always Chris set. So we use this notation mu subscript A for our membership function, in which maps from X to 0 to 1. Alternatively, the function can be like A, for example, X to 0 and 1. This is the function. Here is an example of membership function. We want to define the 7 level of education. If we say 0 is no education, 1 is elementary school education, 2 is high school, 3 is 2-year college, or sometimes they call it as associate degree, bachelor degree, master's degree, and doctoral degree, which is also known as PhD. So in here, you can see that if we consider little educated, this one as little educated, so then if someone has no education, then the membership degree of little educated is 1. So no educated people are little educated. Then it comes to elementary schools. By 80%, they are considered as little educated. And as you can see, it's decreasing, because if someone has a degree, it means he is not little educated. So this is some terminology that we are defining. And if someone has an associate degree, we can't call him as little educated, right? So the degree becomes 0. Then we have educated. So if someone has no education, then 0. If someone has elementary also, we do not consider. But higher school, by 20%, we will consider him as an educated, and you can see increasing. If someone has associate degree, by 60%, we consider him as educated. If someone has bachelor degree, by 80%, we consider him as educated. And if someone has master's degree or PhD degree, 100% he or she is an educated person. And then we have for highly educated. Highly educated is here. So it starts from here up to bachelor degree is not considered. So bachelor degree by 10%, but PhDs are 100% highly educated person, right? So these are how we define membership functions. Several fuzzy sets representing linguistic concepts like low, medium, high. These are linguistic concepts. We often employ them to define set of variables. Such variables are considered as fuzzy variables. For example, temperature is a fuzzy variable. For example, here you can see the membership function of temperature. If you say, for example, this is 0 and this is, for example, 100. 100 is very high, right? So then we have here like 50, here like 25, and here like 75. Then from 0 to 15 is, from 0 to 10 is very low, right? From 10 to something like 40 is low. From, like, you can say 30 to 60 is medium, right? So 50 is medium, okay? 75 is high, and it's very high. So here is membership degree: very low, low, medium, high, and very high. If we have a universal set like X, then a fuzzy set is defined by this function, as I already explained. These kind of fuzzy sets are considered as ordinary fuzzy sets. And on the other hand, we have interval value fuzzy sets. In these sets, the membership function of ordinary fuzzy sets are overly precise. We may be able to identify appropriate membership function only approximately. So we go for this interval fuzzy set. This interval fuzzy set is a fuzzy set whose membership function does not assign to each element of the universal set, but a closed interval. As you can see here, it's a closed interval of real numbers. Those we talked so far are considered as normal fuzzy sets, or we can say fuzzy set type 1, but never they call them fuzzy set type 1. Just they say fuzzy set. They introduced fuzzy set type 2 in 1975. So indeed, why they say that there is some problem with fuzzy set 1, some questions was made about the fact that membership function of the ordinary or traditional or type 1 fuzzy set has no uncertainty associated with it. So to address such issues in 1975, again, Professor Zadeh, he introduced fuzzy set type 2. Like 10 years after the first or initial fuzzy set. Type 2 fuzzy sets and system generalize the type 1, and more uncertainty can be handled using fuzzy set type 2. So using fuzzy set type 2, we can incorporate uncertainty about the membership function into fuzzy set theory. The membership function in fuzzy set type 2 is again fuzzy, but in here we have 3 dimensions, not 2. So type 1 fuzzy sets are working with a fixed membership function, but in here, the membership function fluctuates. So the third dimension that we have, as you can see here, the third dimension is the value of the membership function at each point on its 2-dimensional domain, that we call it as footprint of uncertainty. So in here, x-axis is primary variable, y-axis is secondary variable, and z-axis is membership function value. So in this figure, we can see the fuzzy set type 2. The third dimension that you can see here is the value of the membership function at each point on the 2 others that you can see. The cross section of the slice of the third dimension, also we can see here, the cross section are also FOU. Only the boundary of the cross section is used to describe the membership function of a general type fuzzy set. Here we can see a fuzzy set type 2, and you can see we have double integration. This signifies the union of admissible X and U for continuous interval universal discourse. For discrete intervals, we will go for summation. So you can see here the set of ordinary fuzzy sets, and this one is a fuzzy power set, and you can see here. There are many applications for type 2, right? Like radiology, health estimation for infants, media liveness, behavior detection in smart home, system control, nonlinear systems, seaming clustering. Seaming clustering is one. Also, they call it as fuzzy clustering. In unsupervised learning, this is considered as one technique. Also, in image processing for edge detection, they use fuzzy set type 2. So let's go back to our membership function. Here is one example to better understand the concept of membership function. This is type 1. So we want to have 3 fuzzy variables. One is young, middle age, and old. So using this membership function, we can understand based on our age what people call us. We are young man, middle age, or old. So here you can see this is our first second, and third sets. We have three sets. So this is for young, this is for middle age, and this is for old. Right? If someone is less than 20, so this is years old. 0, 1 year old, 20 years old, 40 years old, 60, up to 100 years old. You can say up to 80 years old. If someone is up to age of, you can say 30, we call young, right? So from 1 to 30, we call young. Then the young is decreasing here, and the age of 30, middle age is a start. And from, you can say 40 to like 50 is degree of 1, then decreases. And old, being old, start from 50, and when it reach to 60, then 100%, we are old, and for more. So this is membership function representing the concept of young. This is young, this is middle age, and this is old. And here is the question. From 0, or you can say day 1 to 20, 100%. From 20, between 20 to 35, we go for this equation, and more than 35 is no young anymore. Then in the second level, middle age, from 0 to 20 and 60 or above, we do not call them as middle age. If someone is between 35 and 45, 100% he is middle age. But from 20 to 30, we will go for this equation, and from 45 to 60, we will go for this equation. Simply you input an age here, 60 minus 8 divided by 50. Then again, if someone is less than 45, we do not call him as old. If someone is more than 60 years old, absolutely he is an old man or woman. And if it's between 45 and 60, then by this equation, we can find the membership degree of being old. The next concept that we need to learn under the context of fuzzy logic is fuzzy relations. Fuzzy relation can be any fuzzy set like R, which is defined on U equal to U1, U2 up to UN. For example, we have a fuzzy logic like R less than on this universe that we have, and U1, U2 are 0, 2, and 20. So in this table, we can see the degree of being less than is our fuzzy variable. So here in this table, we can see the degree of being less than comparatively for each pair in this table that we have. In the first row, we have 0 and 0, you can see. So it's 0, it means not less than. 0 is less than 80 with the membership of 1. 0 is less than 10 with the membership of 10%. Compared to 20%. 60 is less than 70 by the probability of 10%. And 60 is the probability of 20%. 80, right? 60 is less than 100 by the probability of, for example, 70%. 80 is not less than any of this one. So you can see the membership function is totally 0 because 80 is not less than any of those numbers. Many decision making and problem solving takes too much time, and the complexity also is very high if we want to define them precisely. However, people succeeded by using imprecise knowledge, fuzzy logic, that this concept that we are going to talk, and we learn membership and fuzzy sets to come to this fuzzy logic is used to resemble human reasoning, imprecise, not exactly, in use of approximate information and uncertainty to generate some decision. For example, Joe is tall. How we can say he is tall? Or Joe is very tall. How we can clearly define very tall, right? So for NLP, natural language processing, like most other activities in life and indeed in the universe, is not easily translated into the absolute formula of like 0 and 1. So we need fuzzy logic. Fuzzy logic can be interpreted as an approach to uncertainty that combines real value from 0 to 1 and logic operations. Fuzzy logic is based on the idea of fuzzy set theory that we learned so far, and also fuzzy set membership often found in natural language. Unlike statistics and probability, the degree in fuzzy logic is not describing probabilities that the item is in set, but in fuzzy, we say to what extent the item belongs to set. To what extent this one is young, 35, 10%, 28, 80%, 23, 10%, right? Here we have one membership function. Fuzzy values have associated degree in membership, as you can see again. Young from 20 to 40, then middle, then old. We can see here. In order to define membership function, we need to go for some mathematical equations or mathematical shapes or mathematical functions. Trapezoidal membership function, something like this. Triangular is something like this. Or this one can be also like this, or can be like this, right? Trapezoidal. Then we have Gaussian membership function, we have generalized Bell membership function, and also we have sigmoid membership function. So the first one that we use already, triangular membership function, here is the equation. We have to define 3 points, A, B, and C. Then we go for intervals. One interval we have less than A, so from minus infinity to A is one interval. From A to B is one interval. From B to C is one interval. And from C to plus infinity is 1, 2, 3, 4. 1, 2, 3, 4, right? So for interval 1, the membership the degree is simply 0. And for here, from C to positive infinity, it's also 0, as you can see here. But in here, we have to define one equation we need for this one, and one equation for this one. X minus b divided by b minus a for this part, and c minus x, c minus b for this part. So simply, we can define our triangular membership function. The next one is trapezoidal membership function. So we can see here, we need to have a, so minus infinity to a. This is one interval, a to b, b to c, c to d, and d to, so 1, 2, 3, 4, 5. So we define trapezoidal x, a, b, c, d is 0 if x is less than a. Then we have for x between a and b and x between b and c, we go for this one. And for x between c and d and x is greater than d, we go for this one. Finally, we can come with this one. Trapezoidal x mean x minus a, b minus a, d minus a, d minus c, and 0. This is how we can go for this one. Later, I will show you some examples. This is triangular. This is triangular. This is trapezoidal, and this is trapezoidal. Then we have Gaussian membership function. In here, we have c. X is our values. C is mean, or you can say average. S is the standard deviation. Standard deviation is a quantity calculated to indicate the extent of deviation for a group of variables. How close the entire data set is to the average. XP, you know, it's simply e in power of a. For example, if C is 5, S standard deviation is 0.5, then our shape will be something like this. If a standard deviation is 2, you can see, if a standard deviation is 5, it's like, so when a standard deviation is more, it means disparity, right? This example is for inclination degree, right? So if you consider one car, one vehicle, this is one vehicle. So if the degree, the inclination degree is 90, it means it's okay, right? But if it's our turn, then there will be some problem. So this is the Gaussian. So inclination degree, when it is 90, it means it's okay, right? But if it's degree, it becomes something like this, right? Or this part, then you can see the inclination degree. As you can see here, it's opposite. We started from 0 to 1, right? It means when it's 0, our degree is 1. When it's 90, it's okay. It means in the case of accident, when the degree is 90, it means there is no accident. But when it is 1, it means there is some accident. The next one is generalized Bell membership function. Again, we have x, a, b, c. A is width, c is center, and b is slopes. As you can see, 1 divided 1 plus x minus power of 2b. And the next one is sigmoid. Sigmoid is simply x, sigmoid f, x, a, b, c. A is the slope, and this is slope at the crossover of x point c. As you can see from here, we start 0 and the membership starts, and into some parts it comes to 1. So from this part is 1, this part is 1, but here we have some increase. At the beginning of the lecture, I introduced crisp sets and fuzzy sets, which are somehow opposite of each other. Here is the difference between crisp relation and fuzzy relation. So in crisp, we have ordered pairs that show connection between two sets. For example, we can see here A and B. A is related to B, or 2 and 3 are related with, for example, 2 is less than 3. In crisp relations are also sets. So, for example, you can see this one set. However, in fuzzy relation, we have triples A, B, and degree, right? A is related to B with some degree. In here, when we bring it in this relation, means 1 is less than 2, 2 is less than 3, 2 is less than 4. So this is the, what can I say, the relation between these two. And when it is there, it means 1, but we don't have minus 1 and, for example, minus 2, right? Because minus 1 is not less than minus 2. And we don't have 9 and 5 because 9 is not less than 5. So being here, it means 1. Not being here means 0. But in here, we have degree, right? In here, we can have 9 and 5 in case of this one, but the degree is 0. So fuzzy relations are also set. And fuzzy relation can be expressed as matrices. What it means, here is an example of fuzzy relation matrices, color ripeness relation for tomatoes. We want to show the relation of color and ripeness for tomato. If we have 3 colors, like green, yellow, and red, and we have unripe, semi-ripe, and ripe. If a tomato is green, it means 100% unripe, 50% semi-ripe, and 0% ripe. On the other side, when it is red, it means 100% ripe, 20% semi-ripe, and 0%. And in between, we have something between red and green. You can say yellow somehow. So 30% unripe, 100% semi-ripe, and 40% ripe. This is a matrix, right? Simply you can say like 1.50, 0.3, 1.4, 0.2, and 1. This is a matrix. Fuzzy are not learning, but are somehow expert systems. And in the case of fuzzy expert system, we have a collection of membership functions and rules. Membership functions, so far we learned about them. What are membership functions? But what are rules? A set of membership functions and rules. Rules are the second important components of fuzzy logic. Why we need rules? Because we want to reason about data, make some conclusion, inference. or conclusion. The form of rules in fuzzy sets are, we simply call them as if then. If x is low and y is high, then z is medium. It's a kind of rules. We need to define rules. This is why fuzzy system is not famous and is not applicable nowadays, because it needs to define rules, both in artificial neural networks, convolutional neural networks, and many other modern learning techniques that don't define rules. Here is the procedure flowchart of a fuzzy system. The input is crisp. Then we convert using fuzzification to fuzzy values. Then we have fuzzy input. Crisp is converted to fuzzy input using fuzzification, and fuzzification is membership function. This one is changed to x, y, and membership degree. Then we have rule evaluation. This is rule. Rules are here. Rules are here. Then we have some fuzzy output based on inference. Then finally we have the fuzzification. The fuzzification is somehow output membership function. And finally we will have a crisp set. Crisp input, crisp output, but in between is fuzzy. So here is explanation of procedure in a fuzzy system. We start with initialization, and in the first initialization, we define the linguistic variables and terms. Then we try to construct our membership functions and define our rules in our rule base. Then we have fuzzification. Using membership functions, we convert our crisp input into fuzzy input. Then we make some inference or conclusion based on assessment of the rules, based on the rules that we already defined in our rule base. Then we combine the result of each rule and we make some conclusion, some insight, some inference. And finally, we convert to a non-fuzzy values or crisp values to be understandable by machine. We have four main components of a fuzzy system: fuzzification, inference, composition, and defuzzification. So we will explain them one by one. In the process of fuzzification, we deal with the fact base of our system. We need to determine the input and output of our system. Then we need to define our rules, like if-then rules, and then we need to utilize raw data to conclude a membership function. So these are the functions that we do under fuzzification step. Here is an example for fuzzification. Consider an air conditioning system that determines the best circulation level by sampling temperature and moisture level. It means we have one smart air conditioning AC, and it considers the outside temperature and moisture level. Then accordingly, it adjusts the level, right? In this case, electricity bill will be decrease, right? So it's kind of optimization. We want to be comfortable in our room, but on the other side, we want to pay as less as possible. So this system will help us. In this system, the input are the current temperature and moisture, and the output is the level of AC. It should be on non-stop, it means off. It should be low AC, so these are for AC, and high, right? So it means if the temperature outside is good, why it should be high? It should be known, right? Then we can have an acceptable, reasonable electricity bill at the end of the month. So here are our rules. Some rules. We have to define 1,000 rules. If the room is hot, then circulate a lot. It means high. If the room is cool, then do not circulate air. None. If the room is cool and moist, then circulate air slightly. It means low. These are the rules. The next step is inference. In this step, we try to assess our defined rules. Then we try to specify the truth values of the rules. In some condition, there may be an input that does not exactly correspond to some rule. Then partial matching of the input data is used to interpret an answer. So here is an example. Suppose that the system has measured the temperature and moisture level and mapped them to the fuzzy value. Like for example, temperature is 0.7 and moisture is 0.1. The system now infer the truth of the fuzzy rule, right? To do this, a simple method called maxmin is used. This method set the fuzzy value of then clause to the fuzzy value of the if clause. So method infer fuzzy logic from, for example, if the room is hot, then circulate the air lot, so the inference is 0.7. If the room is cool, then do not circulate at 0.1. If the room is cool and moist, then circulate slightly at 0.1. So based on this, the system may infer, for example, this one, 0.7, 0.1, based on the rules that we define. The next step is composition. In this step, we combine all fuzzy inferences that we collected into one conclusion. We have to consider all rules because different fuzzy rules might have different conclusion. Here is an example. Each inference suggests a different conclusion. Rule 1 says high circulation level. Rule 2 suggests turning off air circulation. Rule 3 says low circulation. A simple maxmin method of selection is used where the maximum fuzzy value of the inference is used as the final conclusion. So composition select a fuzzy set of 0.7 since this was the highest fuzzy value associated with inference conclusion, as we have already in this table. And the last step is the fuzzification. So we have input of crisp, we must have input of crisp as well. So what we did falsification, then we had from some rule base and inference, then the falsification will give us this one. So the falsification converts the fuzzy value obtained from composition into a crisp value. And this process is often complex since the fuzzy set might not translate directly into a crisp value. The falsification is absolutely necessary since controller of physical system require discrete signal, not fuzzy. Here is an example, composition output of fuzzy 0.7. The fuzzy output of 0.7 indicates that the air condition should be high, because high is answered. This 0.7 imprecise value is not directly useful since the air condition level is low or high. So the falsification process converts 0.7 to one of these. In this case, it is clear that the fuzzy output 0.7 means high, right? If we got, for example, 0.3, then we may think low. If we got 0.1, we may think of stop. There are many defuzzification methods like adaptive integration, basic defuzzification distribution, and center of area, center of gravity, and many others. So here is center of sum. This is the most commonly used defuzzification technique. In this method, the overlapping area is counted twice. So the defuzzified value, this is defuzzified, we can call it as defuzzified. From 1 to n, xi multiply a, from k 1 to n, mu ak membership value, and this is the membership. So n here is simply the number of fuzzy sets. And mu is the membership function that you already know. This is the number of fuzzy sets, and this n is the number of variables. This is called as center of sums. Here is an example for COS method. We have a1, 1 by 2, multiply 8 minus 1. Finally, we will come to this one, a2, we will come to this one, based on this equation. Here we plotted the aggregated fuzzy set of C1 and C2. So the area, we have a1 and 2. This is one, a1, and this is a2. Right? So the center for C1 is 5, as you can see here. And the center for this one is 6. So we go, and finally 5.35. This is based on this equation. Then we have a centroid method. The crisp value of the output variable is computed by finding the variable value of the center of gravity of the membership function for fuzzy value. The total area of the membership function distribution that we use to represent the combined control action is then divided into a number of sub-areas. The area and the center of gravity or centroid of each sub-area, how we calculate it? We do it and by summation of all sub-areas to find the defuzzified value. If it's discrete membership, we go for summation. Right? Xi multiply mu membership function divided by membership degree. And if it is continuous, we go for integral. X multiply membership degree divided by member. And we go for integral. Here is centroid method. It's a star bar average, right? So for sub area 1, we have 1 by 2. This is sub area 1, right? 1 by 2. 2 multiply 0.5 is the bar divided by 2 is the sum of AI, which gives us 0.5. For sub area 2, this area, we go 7 minus 3, 0.5, which gives you 2. For sub area 3, as you can see here, no, sub area 3 is only this one. We go 1 by 2. Sub area 4 is this part. Sub area 5 is this part. So in order to find the centroids, for sub area 1, we go 1 plus 3 divided by 3, and simply you can find the centroids. And then we will put it here. We calculate AI, XI. AI is area and X bar is centroid of the area. We put here for different sub area. We have totally 6 sub areas. We have AI already, we have X bar, and we multiply. Simply multiply, then we put it here, and we can find as the X star, the falsified is X.008. Weighted average method is another one. This method is valid for fuzzy set with symmetric output membership function. This method is a simple one. It means it does not need very extensive computational resources. And in here, each membership function is weighted by its maximum membership value, and finally the membership is like mu x multiply x divided by sum of mu x. And here is the example. If A is a fuzzy set and it's about a student and the element with corresponding maximum membership value are like this. So if P is passed, F is fair, G is good student, VG is a very good student, and E is excellent, as this set you can see, and P is like 60%, F 40%, G 0.2, very good 0.2, and E like as you can see here. Then the defuzzified value for the fuzzy set A with the weighted average method represent like this one, which gives us F. So what we do, 60 multiply 0.6, right? 60 and 0.6, 70 and 0.4, 80 and 0.2, 90 and 0.2, 100 and 0, right? Divided by 0.6, 0.4, 0.2, 0, which gives you 70. Almost fair student. Why? Why we say this is fair student? because this is 0.4 is for 70 and 0.4 is fair here, so we call this one. The output gives us fair student. Then we have maximum method. In here we consider values with maximum membership. There are different maximum method with different conflict resolution strategy from multiple maxima. First of maximum method, last of maximum method, mean of maximum method. In here we go the smallest value of the domain with maximum membership value, the largest, the Defuzzified. A railroad company intends to lay a new rail line in a particular part of country. The whole area through which the new line is passing must be purchased for right-of-way consideration. It is surveyed in 3 streets, and the data are collected for analysis. The survey data for the road are given by B1, B2, and B3, where the sets are defined on the inverse of right-of-way width in meters. For the railroad to purchase the land, it must have an assessment of the amount of land to be bought. The 3 surveys on the right-of-the-way are ambiguous. However, because some of the land along the proposed railway road is already public domain and will not need to be purchased, additionally, the original survey are so old, like 8060, that some ambiguity exists on boundaries and public right-of-way for all utility lines and all roads. The 3 fuzzy sets B1, B2, B3, shown below, represent uncertainty in each survey as to the membership of right-of-way width in meters in private. So as you can see here, we have fuzzy set B1, B2, and B3, and it gives us this in meter, and this is the membership value. This is the maximum membership value, 0.3, here is like 0.5, and here is 1. So then we can see the fuzzy sets. Now we want to aggregate these 3 survey results to find the single most nearly representative right-of-way width, we can say like Z, to allow the railroad to make its initial estimate of right-of-way purchasing cost. If we combine all, we have this one. If we combine this one, and this one, then we have this one is the composition of these things. Because our data is meter and meter is continuous, then we go for integral using centroid. So to find Z star, using the centroid method, we first need to find the logical union of the 3. So this is the logical union of 3. These are 3 fuzzy sets that we have, and we composite them. We will come up with this one. Now we want to find out the centroid. So from here to 8, and from up to here, we are increasing, then we decreasing. So from 0 to 1.5, something like this, we go for like this. Then from 1 to 3.6, we will go for this one, with 0.3. From 3.6 to 4, we will go for this one. From 4 to 5.5 for this area, we will go for this. From 5.5 to 6, we will go for this one. From 6 to 7, we will go for this one. From 7 to 8, we finally will go for this one, right? So we define based on our degree, we define different rule because we want to find the area, right? We have to divide them, right? For this part, we have this one divided by membership degree, Z is membership, Z is membership. Finally, if you simply calculate this integral, then you come up with 4.9 meter. This is weighted average method, membership degree divided by this one, 0.3 divided, multiply 2.5, center, 0.5 multiply 5 because the centroid is here, 0.5, and 6.5 is the center for this one, divided by this one, which gives you 5.41. Different, right? Different method. And this is min-max method, C star, A plus B divided by 2, 6 plus 7 divided by 2 is 6.5. These are different defuzzification, right? Defuzzification, maybe different methods give us different values. Finally, what we have, we will come up with something, a crisp value, which give us the result. Okay, come to the end. In this lecture, we learn fuzzy logic. First, we will learn fuzzy sets, fuzzy membership function. Then we studied different components of a fuzzy system. Absolutely, this was just a simple introduction. And if you are interested, please ask me. I will provide you more information. Thank you.